Hello class, welcome to this video on AP Statistics, lesson 2.2, density curves and normal distributions. So we're going to look at density curves. So what is a density curve? So a density curve is something that has is a curve that simplifies things. So what it does is it has certain features such as it's always on or above the horizontal axis, and it has an area exactly 1 underneath it. So that's an important feature when we look at density curves. So we're going to look at a specific example of a density curve, which is going to be the normal distribution. And it has to have an area exactly 1. Why does it have to have an area exactly 1? Well, for these curves, we generally use them for probabilities. And we know that probabilities must add up to 1, which is certainty. So it makes sense that we want an area to be 1 when we add up the entirety underneath the curve. And then the area under the curve and above any interval of values on the horizontal axis estimates the proportion of all observations that fall in that interval. So this is basically what I was saying. The area under the curve is the percentage of the observations that fall in that space, right, in that interval. Now, obviously, if you got data only from 0 to 50, and I have the percentage of times that the data falls, if I add the percentage of times from 0 to 50, and that's what my data covers, I should get 100%, right? I shouldn't get anything greater than or less than 100% if I covered my entire data set. So makes sense. So you have to have an area that's 100% or 1 underneath. So let's look at an example. So suppose Selena records the amount of time it's taken for her to get to the bookstore by train each day for the last 1,000 days. The data is recorded in a dot plot of the amount of time that it's taken her to get to the bookstore by train each day for the last 1,000 days. So obviously there's a lot of data here, and this is what she got. So this is the journey time. Sometimes looks like sometimes she took more than 4.5 minutes. Sometimes she took, more than 4.5 minutes. You know, she's got a lot of different journey times, but the most frequent ones are just above 4.5 and then between 3.0 and 3.5, right? Those are the most frequent ones. However, they're not that much more frequent than all the other times, right? So it looks like it's approximately a flat curve, right? It's approximately uniform. So there's a symmetric nature to this data set. So our density curve can be described by a horizontal line. We have those minor bumps in there, sure, but they just happen to occur by chance, right? Based on the data set that we see here. And so we draw a density curve that's completely flat, and so it looks like the area underneath it is a rectangle. And so the height of this, we decide for the height to be 1/3. And the reason why we decide for the height to be 1/3 is because we want the area underneath the curve to be 1, right? So in this case, we say, okay, well, the distance, the range of the data seems to be 3 minutes, right? Because it's 5 minus 2 is 3 minutes. And so we need to multiply that by the height. Well, then 1/3 times 3 is 1, and therefore the area is now equal to 1. Okay, that's exactly what we wanted. So this satisfies what we were saying for the density curve. All right, so there's another example of a density curve, or an example here. So let's look at another example. So the scores of all 947 7th grade students in Gary, Indiana on the vocabulary part of the Iowa Test of Basic Skills, ITBS for short, are graphed on a histogram. Okay, so we're going to graph these results. And so you got your histogram, and we superimposed a curve on top of that. And that curve is going to be our density curve. All right, so the histograms obviously are just the bars, but we superimposed this density curve over it. This seems to be a good estimation of what's going on in that data set. Now, is the area under this curve 1? Well, we know that this is a smooth curve, and we know that it is above the horizontal axis. This curve never goes below the horizontal axis, and it actually never touches the horizontal axis. It looks like it touches it eventually, but it will not. It will only touch it at infinity, which means never, right? And then here, it'll only touch it at negative infinity on that side. So it actually continues to get smaller and smaller. That's the idea of this curve anyways. And the area of this curve, this is actually a bell-shaped curve, and this has the feature that the area is actually 1 underneath it. So if I were to do this, even though this curve goes on forever, right, it actually does have an area equal to 1. Okay, so that's something that we can prove if we look at the equation of this curve and use a little bit of calculus. You can prove that the area is equal to 1, and it's called the Gaussian distribution. And so that you can look up the formula for the function of the Gaussian distribution, and then you can integrate it. But in any case, this is a density curve. So the mean of a density curve is the point at which the curve would balance if it's made of solid material. So the mean of any distribution is the balance point. Okay, so that's important to realize. The mean is the balance point of any distribution, right? So in this case, the mean of a density curve is the same. It works the same way. It would balance it. So if you have a curve that's made of solid material, where would you balance that object? And the median of a density curve is the point that divides 50% below and 50% above, right? So it cuts the curve in half. So in this case, we have a normal distribution, a Gaussian distribution, a bell-shaped curve, right? So we got normal distribution. It's also called Gaussian after Carl Friedrich Gauss, mathematician, a physicist. Let's see, and then we have so normal, Gaussian, and then bell-shaped, right? So those are just some names for that. But it's completely symmetric. So we know that we can balance it in the middle. And so we know that the mean and the median should be at the halfway point. We can balance it in the middle, and not only that, 50% of the curve is above, and then 50% of the curve is below. So it matches both. So the median and the mean are the same for a symmetric density curve. They both lie at the center of the curve. When we look at this curve, this is not a symmetric density curve. We want to keep in mind that it's skewed here. It's skewed right. Skewed to the right. Which means that what's going to happen is that the median, this is going to be 50% of the curve here, and 50% of the curve on the right side. But the mean has to be balanced. The mean cannot be balanced where the median is, because we have outliers or whatever stuff going on the right side. So the mean is going to be pulled to the right of the median, okay? So the direction of the skew, that's going to be the direction that the mean is going to be pulled in, all right? So if this were skewed to the left, we would expect that the median will be where the 50% mark is of the data, and then we would expect that the mean is going to be pulled in the direction of the longer tail. So then we would expect that the mean would be somewhere here, perhaps, right? So just something to keep in mind. So the mean of a skewed curve is pulled away from the median in the direction of the long tail. Okay, so let's look at let's take a look at that same graph, the one that's skewed to the right. And so keeping in mind that a density curve is an idealized description of a distribution of data. So it's an ideal description, it's not the exact description, right? It's the curve that best describes the data, but also has the features that has an area equal to 1, etc., right? We distinguish between the mean and standard deviation of the density curve and the mean and standard deviation computed from the actual observations. So there's a difference between the mean and standard deviation of the density curve, and then when you do this from the actual observations, because remember, the density curve is ideal, right? The usual notation for density curve is mu for the average. That's the Greek letter mu. And then standard deviation of density curve is lowercase sigma. That's the Greek letter lowercase sigma. One particular important family of density curves are what we call the normal curves, the Gaussian distribution curves. That's what we were mentioning earlier. So the Gaussian distribution, the normal distribution, bell-shaped distributions. So notice that what distinguishes these two curves here are the where the mean is and the standard deviation. So that's what perfectly describes the normal curve, by those two parameters. All right, so the shape, they all have the symmetric single-peaked bell-shaped. Their center is mu, and then the spread is sigma. Okay, and the mean is equal to the median here because the mean is equal to the median here because it's symmetric, and the variability is determined by sigma, the width. Okay, so normal distributions, as we mentioned, they're symmetric, single-peaked, bell-shaped. We call it a normal curve, normal distribution. Any normal distribution is specified by those two parameters, mu and standard deviation sigma. So this is the notation, the capital N for normal, and then you have your mu and your sigma. So normal distributions are important because there's lots of examples where you can use it to model distributions. So for example, if I'm looking at SAT scores, IQ scores, generally they tend to be clustered. They tend to be normally distributed. So if I were to graph them, they would have like a normal bell-shaped curve to them. And the reason being is that most people score in a certain range, right? Average. And then you have the extremes that score really low or really high. Any characteristics of data or any features of data where you see this stand out, right? There's a lot of examples that stand out in this way, where you have most people are on average a certain value, and then you have extremes on either end. So therefore, very important to know the normal distribution. Okay, this is also, this can also be modeled with phenotypical characteristics. So in biological populations, like characteristics, like for example, wing size in certain insects or whatever, whatever features you can think of. In biology, you tend to have, if you're talking about, for example, wing length or something, you might have on the average wing length here, where most insects have a certain average wing length, right? And then you might have some extreme insects, right? You may have a few that have really long wings or really short wings. So that's on this lower and upper end, right? Now these, so the ones here, they were, if you think about natural selection and things like that, or whatever, these, are the typical wing lengths for that particular population because there's an advantage to that. And then you have a few that have long and short. All right, so in this case, let's take a look at another example. So another example would be, for example, if you had chance outcomes. So if you had proportion of heads and tails, we know that if we were to graph this, it would have a good shape that is normal. So let's look at more normal distribution characteristics. So all normal curves have this property in common, which is the empirical rule, also known as the 68, 95, 99.7 rule, for obvious reasons. If you look at the definition here, or if you look at the the description, it says that if you have any normal curve, then if you go out from the center, which is the mean, if you go out one standard deviation to the left and one standard deviation to the right, you're going to cover 68% of the curve. Okay, so 68% of the curve is within one standard deviation. If you go out two to the right, two sigmas to the right and two sigmas to the left, you're going to cover 95% of the curve. You can see that most of the curve is covered in that region. And then if you go out as far as 3 standard deviations to the right, 3 to the left, you're going to cover almost 100% of the curve. Not quite 100%, 99.7, right? And so there's a little bit of extra in the tails here, because remember the tails go to infinity, right? On positive infinity to negative infinity on either side. And so there's still a little bit of area there. So pretty interesting. This is something that you're going to want to know. So for using these numbers, you can come up with the percentages for each of the areas underneath the curve that are marked here. So for example, if I just focus on that graph, we know that these two parts have to both be 34% because the entire thing is 68% and there's symmetry. So it's going to be 34%. On the other sides, these ones here, they're going to be the same because there's symmetry. And in order to find them, well, we know that we know that it's 95% from there to there, right? And it's 68 from here to here, and so you could subtract. You could say 68 subtracted from 95, so you could say 95 subtracted, or 68 subtracted from 95, that's 27, and then you're going to divide that by 2 because it's split on both sides, right? And so that's going to be 13.5%. All right, and then you repeat for the other one, so you say 99.7 minus 95 because you're trying to figure out that 95% part and then the 99% part and then the 95 part. You want to subtract those, and then divide by 2. And so if you subtract that, you get 4.7 and then divide that by 2, so you get 2.35, right? So 2.35% on either side. And then to get these parts here, you're going to need to subtract 100 or 99.7 from 100, because remember the rest of it is going to be 100. So you got 100 minus 99.7. Well, that's going to be 0.3%. Then divide that by 2. So that's 0.15. So the last parts are 0.15. Okay, so you're going to want to know each of those percentages, or at least how to find them. At least know the 3 basic numbers, and then from there you can get the rest. So this is a property of all normal distributions. Okay, it must follow this rule. So if you wanted to test if something if a distribution is approximately normal, you can follow this. It has to follow this rule, right? So if you're 1 standard deviation out on either end, it's got to cover 68% of the data, and so on and so forth. So it's a good way to test normality. Empirical rule also works with standard normal distributions. Standard normal distribution is when the center is 0, the mu is 0, and your standard deviation is 1. So notice that we're going by ones here, right? So again, the mu is 0 and the standard deviation is 1 in a standard normal distribution. Okay, so it's a special type of normal distribution, but it works the same way as far as the empirical rule. Okay, so again, this only applies to normal distributions. So if I look at an example, the distribution of Major League batting averages has a mean of 0.261 and a standard deviation of 0.034. So we got our mu and we got our lowercase sigma. About what percent of MLB players had batting averages of 0.363 or higher? Well, let's label this on our curve, right? So we know that that's the mu and so on and so forth. So let's do that first. The middle is going to be 0.261, that's the mean. And then we're going to add 0.234 to that, 0.034 to that, and subtract 0.034 to that, okay? And we get 0.295, 0.227. And then we're going to keep doing that, right? To get those 2 numbers, and then keep doing that again. Keep adding point and subtracting 0.034. You get those numbers. All right, so that's how you label the x-axis for this, right? And then now we want to look for, okay, we're looking for 0.363 or higher. So we're looking for this, right? So 0.363 or higher. Well, that leaves us with this section of the curve, right? 0.15. And so that's our answer. It's 0.15%. Had a batting average of 0.360 or higher. So the probability or the proportion, so this is the proportion or the probability that x, right, that the score, we're saying that the batting average is x, is greater than or equal to that 0.363 is 0.15%. Okay, so that's how you write out with the symbols. Now, we're looking for 0.22. It says a player with a batting average of 0.227 is about what percentile? So 0.227 is, well, we know it's here, right? So the percentile is percentage of people that are at or below, right? And so we need to add these 3 areas to get the percentile to the left, right? The area to the left of 0.227. So it's going to be adding those 3 numbers, and that's going to be 16%. So we're at the 16th percentile. All right, so let's look at finding areas for proportion less than. So there's 3 cases that we have. We have where we had to find an area where proportion is less than. We had to find area where it's between 2 z-scores, and we had to find the proportion greater than. Okay, so there's those 3 main cases. So if I look at the ITBS example, Remember we said that it was approximately normal, right? Because it was a histogram that was approximately normal. So we can model it with a normal distribution. The mean is 6.84, standard deviation is 1.55. What proportion of these 7th graders have vocab scores below 6th grade level? In this case, 6th grade level is a score of 6. So first step, you're going to want to draw a normal distribution, right? Label your mu, go by, add sigma, right? You keep adding sigma as you go and subtracting sigma as you go, right? That's what we have there. And then we label our score of 6. Our score of 6 is here, right? And we show a dividing line so that, and we said we want them to be below. So that's the area to the left, right? So we have to shade the area to the left for it to be below. All right, so there's our area clearly shaded. There's our normal distribution clearly labeled. So now step 2 is to perform the calculation. So we need to convert the scores into a z-score. All right, so you're going to want to use the z-score formula. All right, we've done z-scores before. I'm giving you the formula here again. We've done it in the last lesson 2.1. So we're going to calculate the z-score for this. So how do we do that? Well, we know that the x value, the score has to be 6, right, below 6th grade level. So at the 6th grade level or below. And then we got the mean is 6.84, and then the standard deviation is 1.55. We calculate that, we get a z-score of negative 0.54. You're going to round this to 2 decimals, right? So why do we need to convert to a z-score? Well, because we need a table in order to find the area. The only way we're going to find the area underneath that curve is if we use a special table, and this special table uses z-scores, right? So we need to convert it to z-scores. We'll show you that table in a second. So this is the table that uses the z-scores. This is the standard normal distribution table. You have this on the AP exam. So you'll have the reference page with all of the values for certain z-scores. You're going to get, so this is, for example, this is read as if you got a z-score of negative 0.63, then your area under the curve is 0.2643. That's just an example, okay? So for this example, our z-score was negative 0.54. Notice that I converted this to a standard normal distribution. This is now a standard, right? Because it's 0 and it's going by ones, right? So this normal distribution is converted to z-scores. So now we got negative 0.54 here. We need to look that up. Well, that's going to be here. That's negative 0.54, right? Negative 0.54. And so that means that my area here has to be 0.946. 2946. Okay? So that's how you use the z-table to find the area. All right, so then the proportion of values, or the probability that the z-score is less than the negative 0.54 is 0.15%. Or not 0.15%, I'm sorry. We need to change that. So this is going to be 29.46%. That's from this value here, right? The 0.2946. All right, so here we go. So this is how the table looks like. So this is how the standard normal distribution table that you'll get in class. That's how it looks like, right? So you can look this up. If, AP statistics, standard normal probabilities table. You can get this. And this is widespread on the internet. So you type in standard normal probabilities table, you'll get a table with the z-scores and the area. All right, so that's how it looks like. Now this table gives you the area to the left, so keep that in mind. It always gives you the area to the left. It never gives you the area to the right when you're looking at the standard normal probabilities. Okay, so you want to keep that in mind, that these areas reported here are the areas to the left of the z-score. So that's important to know. All right, so that's how it looks like. Let's show you with technology. So with technology, we can use a function called normal CDF, right? Normal CDF. And you have to, I will show you where to find this function, but you provide the lower value, you provide the upper value, the mean, and the standard deviation. So for example, in this example, we were doing a normal curve with a value of negative 0.54 here, right? That's the upper value because we want to do this area here. The lower value is actually negative infinity, but you can't type negative infinity on the calculator. Negative infinity is not a number. So we type in a really, really small number, or if you think about it, a really, really negative number, right? So negative 1,000 is fine. Negative 1,000 is more than enough. So negative 1,000, negative 1,000,000, whatever you want to type it there. But it has to be a pretty large number, but negative, right? And then we have from there to negative 0.54. And then our mean is 0 and our standard deviation is going by ones, right? So that's what these are. And we get the same answer, 0.2946. So let's show you this on the calculator. So we're going to hit second, vars. Then we're going to go down to normal CDF, number 2. Then we're here that it types in -1 with 99 zeros. You don't have to do that. You could just type in negative 1,000 for the lower. For the upper, you're going to type in negative 0.54. There's your 0 and your 1. And we paste that. And so in this example, the calculator used -1 times 10 to the 99th power, right? So that's a really, really small number. But that's perfectly fine. So negative 1,000 is more than enough, like we said. All right, so now that we finished doing it on the calculator, now we're going to answer the question in context. That's step 3. So now we're going to answer with the area that we got before, which was 29.46%. So we're going to say about 29.4% of Gary, Indiana 7th graders scores fall below the 6th grade level on the ITBS vocab test. So this is answering in complete context. Remember, you do want to answer it in context, because if you answer this, for example, on the free response, then one of the things that they score you on in the rubric is, did you include the context? So definitely want to make sure you practice that from the get-go. So now let's take a look at an example where we're doing between two z-scores. So same ITBS example, but this time we want to figure out what proportion of these 7th graders have vocabulary scores that are between a 6th grade level and an 8th grade level. So that's between a score of 6 and an 8. So I went ahead and labeled this for step 1. I did the normal distribution just like we did in the previous example. This time I marked 6 and 8 on the graph, and I want to shade the area between them since I'm looking for the proportion between. So this is step 1. So now if we look at step 2, we're going to perform the calculation. We have 2 z-scores that we need to calculate, one for the 6th score and one for the 8th grade score. So using the formula twice with 2 different values for x, 6 and 8, we are able to calculate the 2 z-scores. These 2 z-scores can be put on the graph as well, so that you can kind of visualize it. If you put it on the standard normal distribution, that's the graph that starts at 0 and goes by ones. So I show that here. So you can see the graph where it starts at 0. So this is called starts at 0 and it goes by ones, right? That's called the standard normal distribution. And I graphed and I showed my 2 z-scores. So I showed my z1 and my z2 right there. Okay, so now we're going to use the table A in order to locate the area of the 2 z-scores, right? So let's look at z1. So for the first one, negative 0.54. We're looking for these two, negative 0.54. So this is going to be my area. That's the one that we got, the area that we got earlier. But remember that represents this area right here, the area to the left. Now if we go to the other one, so this is the 0.2946, and that represents from here to here. Now if we look at the other part here, the 0.7734, that represents the area from here to here. So 0.7734. Okay. Now how do we get the area in between? Well, to get the area in between, we need to subtract the two quantities together, and that gives us the area in between. So the area here is 0.7734 minus 0.2946, and that's how you get the area, the shaded area. Okay, so hopefully that that makes sense from what we from the picture. Okay, so now if we show the work here, we got the probability that z is between those two z-scores is going to be obtained by taking the difference of those two scores, of those two areas. So we get an area about 0.4788. All right, so let's look at the calculator example. So if I wanted to calculate this using the calculator, I need to use the normal CDF function, just like I did before. But this time, by the way, the CDF here, CDF means cumulative. You know, the C stands for cumulative, so you're doing a cumulative distribution. So the cumulative density. And so what that means is that you're taking the values from left all the way up to that value and you're adding them together. Okay, so essentially what you're doing in the chart where you're adding the areas up from the left to the boundary, that's a cumulative. That's what we're doing when we're doing the cumulative, you know, percent. And so that's why we use the CDF function. Now, so we need to provide a lower value and an upper value. So in this case, the lower value is the z-score was negative 0.54, if you recall, and then the upper value was 0.75. Those are our two in-between values. And if we do that, notice that we get the same answer. Okay, so answer the question in context. So if I so now we have both graphs. We have the original normal distribution, and then we have the standard normal distribution, the z. So if we answer the question in context, we say that about 47.9% of the 7th graders from Gary, Indiana, fall between the 6th grade level and an 8th grade level. And there shouldn't be a question mark there. I don't know why it's that's there. So it should be a statement, not a question. All right, so now let's look at the third case where there's proportion greater than. Again, using the same ITBS example. This time we're looking for the proportion of 7th graders with a vocab score above 6th grade level. All right, so we draw a normal distribution and we shade to the right since we want it to be greater than. And next we perform the calculation. We have the same z-score that we had before, and that makes sense because it's the same 6th grade score, right? So it's the same z-score. So we have negative 0.54, and we're shading to the right of that. This is my z-score value, the negative 0.54. We look it up, of course, and we get 0.2946. That represents the area to the left side. Remember, the table A always gives you the area to the left. If you want the area to the right, well, remember that the two areas, for the area under a density function has to always equal 1, right? And so that means that that's the same thing for the normal distribution. The area under the normal distribution has to equal 1. So that means this has to be 1 minus that number. So 1 minus 0.2946 is going to give us our answer. So we got the proportion of the probability that z is greater than negative 0.54, that's how you use the symbols, is equal to 1 minus the probability that it's less than, which gives us 70.5%. All right, so now if I use the normal CDF function, of course my lower value, here in this case our lower value is now negative 0.54. This is our lower value, and we're shading to the right of that, right? So we're shading, so from the left to the right, we're going from negative 0.54 all the way up to infinity. And of course, can we really get it to infinity? And the answer is no, because that's not a number. So we type in 1,000 or something like that, and a number that's big enough where it should be more than enough. And so we get the same type of result. All right, so now answer the question in context. So this means using our answer, 70.5% of Gary, Indiana 7th grade scores fall above a 6th grade level. Those are our three cases: less than, between two scores, and then greater than. Right, so now what happens if we work backwards? So let's find the value from the area. So this time we're going to be given the area, and then from that obtain the value. So this is like the reverse of the situation that we just did. Okay, so according to the CDC website, the heights of 3-year-old females are approximately normally distributed with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. 75% of 3-year-old girls are taller than what height? All right, so first off, we're going to draw the situation. We're going to draw a curve where it's a normal distribution. The center is 94.5 centimeters, the mean. And then we're going to add 4 to the right, and then subtract 4 on the left side. So we got our bell curve. We have our mean, mu, right? And then we are adding by sigma, right? Sigma is 4 centimeters. And this is our mu. Okay, so we're adding 4 and subtracting 4 on either side. So this is these are the set of values that we have. And next we mark what they want. So they said 75% of 3-year-old girls are taller than one height. So we don't know what the height is here on the x-axis, so we're just going to say it's x. But we know that it has to be somewhere here where the area to the right, where it's taller, is 75%. So we have to work backwards in order to get what the x is. Now, first off, we know since this is the area to the right, that means the area to the left has to be 0.25, has to add up to 1. We're going to use this area here to look up in the z table, in the table A, in order to get the z-score. Okay, so using this area, we are going to look up using table A, what is the closest area to that? Well, if you look at these sample values provided, the closest value to that is 0.2514. That's the closest area to what is provided here. Remember, we want to look up the area to the left because the table gives us the area to the left. So that's the closest value. And therefore, our z-score seems to be approximately negative 0.67. So you can see that from the table. So we're working backwards here. So that's my closest area. So my z-scores are provided, negative 0.67. Okay, so we're going to show you how to do this on the calculator. So first off, using the normal CDF function. Okay, so I want to go ahead and make a correction. So we're not using the normal CDF function here. So I went ahead and corrected it. So we're using the inverse norm function, okay? So the inverse normal distribution. Normally, the normal distribution function, the CDF, it gives you the area, right? This time we're going backwards, the inverse of that. So given the area, can we find the value that corresponds to that? So here you had to provide the area, the mean of the distribution, and the standard deviation. Here we're looking at the z-score, and so we're using a normal distribution with a mean of 0 and a standard deviation of 1, okay? That's the standard normal distribution for z's. Okay, so now that we got that, we know that the area is 0.25. It was the area, in this case, it was the area here, right? If we shaded it in the previous step, it was 0.25. So we provide that there. We provide the 0 and the 1, and we get negative 0.67. So we'll show you this on the calculator. So here we're going to hit second, and then vars for variables. We're going to go down to inverse norm, and then put our area, 0.25. And then the mu is 0 and the sigma is 1, so we can just paste that. And then notice that this is how the function looks like on the calculator. You can hit enter, you get negative 0.67 for my z-score. All right, so now let's take a look at step 2, where we're going to do this. We're going to calculate the z-score here. Or the x value rather. We already found the z-score was negative 0.67. So first off, we're going to take the z-score formula and we're going to solve for x. So we're going to solve using literal equations, right? So what you would normally do in algebra 1, and we're going to solve for x. So we're going to multiply both sides by sigma in order to solve for x. And then we're going to add mu to both sides to get x by itself. All right, and that's how you get the equation. So this is the equation that we're going to use to get x, the value from the z. So we know what the z is, we know what mu and sigma are, so we can easily find x. So when we plug in, we get mu is 94.5, standard deviation is 4. We know that the z-score was negative 0.67, so we're going to use that here. All right, so now we have enough information. We can plug it in and get x is 91.82 centimeters. So that means 75% of the girls, of 3-year-old girls, are taller than that height, 91.82 centimeters. So let's interpret this in context, of course, but first let's show you how to do this using the calculator. So we've shown you how to use the calculator, the inverse norm function, to get the z-score, and then plug it into the or solve for x in the z-score equation to get an answer, right? The 91.8. How can we get to the 91.8 directly on the calculator? Well, you provide the same area of 0.25, but this time instead of the 0 and 1, you're going to provide the mean and the standard deviation. We know that from the problem. And then you get 91.8 directly. Okay, so we've shown you essentially two ways to do this. So if we go ahead and interpret, and we'll show you this on the calculator. So we go second vars, we go down to inverse norm. All right, and we provide our area of 0.25. And then this time we replaced the mu of 0 with 94.5. We replaced the sigma with 4. We paste the results, we enter. Of course, we're just going to show you how the function looks like. And then 91.8-ish is my answer. So we get our x value is now 91.8. That's what gives us the area of 25% on the left, 75% on the right. So our answer is about 75% of 3-year-old girls are taller than 91.8 centimeters. All right, guys, that's going to do it for the video. I hope you learned something. I hope you found this useful, as usual. I'll see you in the next one.